Yeah, I hope I look enough like a crazy scientist. My wife always tells me my hair looks kind of terrible, you know, but okay, welcome everybody, good morning. Some of you guys have seen me this morning already at our stand at Moritz State at the Space Science Center, because what I want to talk with you guys this morning is a little bit more going into some kind of a revolution that we're having seeing right now in Kentucky, a transition that we are seeing from low-tech into high-tech. And the cool thing is you guys can be all part of that. What do you guys think is the #1 industry in Kentucky? Huh? Coal? Coal, okay. Bourbon, awesome. Okay, what else? Horses maybe, yeah. Huh? Yeah? Okay, let's look at this. Coal. No. Horses. We like horses, correct? Cool animals, really nice. Are they the biggest industry? No. Bourbon. Yes, bourbon is cool. Yeah, I know. Go on the bourbon trail, great fun, you know, but no. Everybody likes a Corvette, correct? Yes, that's cool. I want a Corvette, correct? You probably want one too. Big industry, but guess what? No, not at all. You won't guess it? Before I came to Kentucky, I had no idea what the #1 industry was. It is space. Can you believe that? No. You people don't think about this Kentucky as an aerospace industry, but it is. It is a $11.7 billion industry. It was about $12 billion industry last year. Kentucky is #3 in the nation, believe it or not. I mean, there's Washington State with Boeing. You cannot beat them. They have about $60 billion. Try to get to this. California is next, but 2016, Kentucky was #2. We got beat by California just barely again last year. But it's a $12 billion industry, and all the other ones are just barely making it. By the way, bourbon is also about $5 billion. Horses is about $3 billion. So it doesn't even get close to this. So it is our aerospace. And aerospace is invading our life more and more. There are something like 600 companies in the Lexington, Louisville, Cincinnati area that produce aircraft parts. Like brakes from aircrafts are coming from Lexington. Turbine blades for aircrafts are coming from Louisville. All these parts are produced in Kentucky. And we have a building space industry. We have industries like they launch things to the International Space Station. There's Space Tango, for example, that brings stuff to the International Space Station. And what I want to talk with you guys about today is stuff we do in Moorhead. We build our own satellites. We have our own satellite program, and I will introduce you a little bit to this. Because satellites, what was Earth's first satellite? Thank you, the moon, exactly. Yes, you're right. The first one that was man-made space, the first man-made satellite, of course, was Sputnik. That was launched 60 years ago, and that gave the beginning, basically, of the space era. After that, we had the space race, in particular in the 60s. Then it calmed down a little bit in the 70s. First of all, in the 60s, everybody thought space is cool. You want to go to the moon, that was it. And once we went to the moon, things got a little bit boring and calmed down a little bit. But you know what? Who of you guys have used a satellite today? Everybody. Probably some of you guys are texting right now and using a satellite, correct? I caught you. Yes, okay. So everybody is using satellites today. No matter what you do, if you use a satellite, if you check the weather, if you go on, watch something on Netflix, whatever, you guys are using a satellite. So satellites are becoming part of our life, even if we don't even think about it. But they're becoming a bigger part of our life. So they're everywhere. It means defense. The defense industry is, of course, a big one. Telecommunication. Your cell phones wouldn't work without satellites. You couldn't call somebody in Europe if there wasn't for satellites. Yeah, they are underwater cables, but what's the capacity of those? Broadcasting, everything, navigation. We all have our GPS on the cell phones, correct? So you know where you go. You have GPS in your car. All these things are supported by satellite. And last but not least, we will eventually get also space tourism. You might go into space just for the fun of it. It's still expensive, but you probably at some point can do this. And we have links to the internet, all coming from space. But when you talk about satellites, typically, what are you thinking about? You think about big satellites, correct? You think about something like this. You think about telecommunication satellites. They are the size of a school bus. And they're expensive. Hubble Space Telescope. Well, the Hubble Space Telescope, the space shuttle was designed for the Hubble Space Telescope. That's why this thing is as big as the space shuttle. That's why the payload bay in the space shuttle was that big that it could fit a school bus, because the Hubble Space Telescope had to fit into this. Billions of dollars. Big satellites. Or GPS satellites. Okay, they are smaller ones, but they are still significantly in size. However, these satellites are large, correct? School bus size, the cost of these things are hundreds of millions of dollars, at least. Some of these, like these telecommunication satellites, are billions of dollars. Hubble Space Telescope was $1 billion. We just heard the other night that the James Webb Space Telescope will be delayed by another year, will be launched now in 2020. That thing will be about $8 billion. So these things are expensive. The other problem is when you deal with these big satellites, to build those things, you need hundreds, you need thousands of people to do this. The next big thing is small. We can do much better, we can do this much smaller with CubeSats. We can do this with miniature satellites like this one. And some of you guys were there this morning at our stand with Kennedy, and you have seen this one. If you have not seen the satellite before, maybe you have a chance this afternoon coming back to our stand and to our booth and touch a satellite, pet a satellite if you like. Our satellite petting zoo is out there, so if you want to touch this thing. This is a real satellite. All the components we have on the big satellites is in this small one as well. So we have a radio, we have the power supply, computers, we have ways to steer this thing in the Earth magnetic field. We have a detector in here. Same detector that your dentist is using to x-ray your teeth is in the satellite. So we do use these for scientific explorations. We can use them for going to the moon, and I will get to this in a second. I will get to this later on. We will go to the moon. Now, why do we do this? Why are we going to small things like this? Well, the other ones are much more impressive, correct? If you have a Hubble Space Telescope as big as a school bus, well, that's an impressive thing. They cost billions of dollars, again. These things are much easier. These things are much easier to build, much faster to build, and they are cheap. When I'm talking about that satellite over there that some of you guys held in your hand this morning, that's about $500,000. Now, that's still a lot of money. I mean, I don't have $500,000. I will never have $500,000 in my life. However, for a satellite project, this is cheap. So universities can afford it. And we go even a step further. We go into the pocket cubes. We will talk about ThinSats in a second, which are even cheaper and cheaper. It becomes cheaper and cheaper. CubeSats were invented by this gentleman over here, Bob Twiggs. He is one of the professors we have in Moorhead. He retired from Stanford about 10 years ago, and then, hey, retirement is boring, correct? You don't want to retire. So he came to Moorhead and helped build up the space science program that we have. He invented those in the 1990s. And first people thought, that's just toys. I mean, yes, we all like to play with toys, but that's just nonsense. You know, why would you bother with this? Well, guess what? Yes, you do want to bother with these things because they are cheap. You can test out new components, what you cannot do with the big satellites. If you lose a $100 million satellite, you lose $100 million bucks. If you do this one, well, what do you lose? Not much. You lose $1 million bucks maybe. Who of you guys have a computer with you right now? I do. Right here. Everybody does, correct? Because we all use smartphones these days. That's a computer. This thing, even my little $10 smartphone, yes, this is $10. This is not an iPhone for thousands of bucks. This is $10. Kroger's had a deal on that thing. That's $10, and that has more computer power than the Apollo missions had. And we have it in our pockets these days. That's thanks to the miniaturization that we have in the computer industry. And this miniaturization makes it possible for us these days to deal with satellites like this, to deal with satellite missions that can fit all the components you have on the big one into these small little boxes. But these small little boxes are challenging from an engineering standpoint because you have only so much room. And you have a mass constraint. You can only bring 2.5 kilograms on these what we call CubeSats, the tube cubes, into space. That's it. And that's your challenge. If you want to go into an engineering program like this, that is your challenge. That's what you have to do. is problem solving. You have to learn problem solving as well when you go into programs like this, because you have to figure out, how do I make this work? Because this satellite has to have a purpose. It's not just we launch something and then it's up there. This one has to measure X-rays, for example, from quasars, from supermassive black holes. How do we make this happen? That's your challenge. You have to design it, you have to build it, you have to integrate it, and you have to test it so it has to survive in space. And we do this. This is becoming a much larger industry now. Since 2000, we have launched about 1,700 CubeSats into space. Now, these things don't stay long in space. They usually stay for about a year in a low Earth orbit, then they disintegrate in the atmosphere. But you can see here, this is the curve, how it increased. It's projected that by about 2020, we will launch about 500-600 per year. It's a growing industry. Most of this stuff is still coming from the industry, but the university, when you look at this, universities, schools can launch satellites because they become cheaper and cheaper. What are the costs? And what are the applications here? Let's talk about the applications first. Now, when you use GPS, if you're in a city, you sometimes have a problem with the GPS signal. The problem here is if you don't see 2 or 3 satellites, you don't get your position, because from one, you need at least 3 satellites to have the position right for where you are, to get the signal from 2, 3 satellites. If you have only one, well, you're out of luck. So if you have a shading from buildings or mountains and so on, because here in Kentucky we have a lot of mountains, correct? So if you're in one of those hollows, you are out of luck. You may not see a GPS satellite, or you not see enough GPS satellites. If you have, however, hundreds of little CubeSats up there, you will see them. The other advantage is disaster management. Sometimes we have, like, for example, we have an aircraft crashes on Earth. We have an aircraft accident. But typically they happen, of course, in regions where you cannot reach the people easily. Now with the big satellites, we only have a few. That takes you days that satellite is over a specific position, If you have a CubeSats, if you have an armada of CubeSats, you have them there in an hour. Because so many CubeSats, if you have hundreds going around the Earth, one of those CubeSats will be at the right position, and you can figure out what's going on there. Fire, floods, whatever, any kind of disaster management, this is important for these things. The launch of these CubeSats is also much cheaper than when you launch a big satellite. So typically, when we launch a CubeSat, we are talking about the whole thing, including launch like this one, is about $500,000. The whole project is about $1 million, because you usually build 2 satellites. One is the engineering model, the other one is the flight model that actually goes into space. Typically, you can say the launch cost for 1 cube is about $100,000. If you deal with a 3 cube, which is 3 times, which is a little bit longer than this one, that's 30 centimeters long, we are talking about $250 million. So you can make this for less than $1 million. It goes even cheaper. These are pocket cubes, which are only 5 by 5 by 5 centimeters, so about 2 by 2 by 2 inches. And you can launch them, including everything, for $50,000. That's still a lot of money. I don't have $50,000, but you can even make it cheaper into ThinSats. And ThinSats is the new development where you launch 24 of those satellites together. And then we are talking, with including everything, $25,000. A school can afford that. Now you will say, we don't have the money for it. You will see when schools do fundraising projects, they come up typically with something like $12,000, $13,000. So you do basically 2 bake sales, you're done. You have something into space. Think about that. It's easy these days. And again, you can test new components. Now, this is our facility at Morehead State. So we have a space science center there. It was erected in 2009. It was opened 2009. And we have a lot of facilities in here which really surprise you, because before I came here to Kentucky, I had no idea what was here. I was same as you. Coal, maybe horses, bourbon, that's it. But that we have a space industry, I would never thought about this. This facility has a 110-seat digital planetarium. We have a clean room. We have testing facilities that allow us to test space components. And we have launched several components into space. That's our clean room over here to the left. So we can integrate satellites that go out in space. We can manufacture the satellites. We solder the solar panels, bring the whole thing, build the whole thing together. That satellite over there was built by our students. It's not an industrial product, but students can learn. You guys can learn everything. because these small projects only involve something like maybe 20 students, 30 students at most. So you can learn everything that goes into a satellite project. If you're on a big satellite project, we are talking about, as I said, hundreds, thousands of people. You only do a little tiny part of that satellite. With this one, you do pretty much everything. Testing is very important. We do testing. We have for example, we have this anechoic chamber, which is unique to Kentucky. It's the only one in Kentucky. And what we do with this thing is we can test satellite in a space environment, the radio environment in space, because you don't have reflections in space. We have these absorbers all around this chamber, and we can test how the antenna of a satellite behaves. Now, why is an antenna important? Well, your cell phone has an antenna, correct? You don't realize that, but your cell phone has a microwave antenna inside. Otherwise, you couldn't communicate. And that's the same thing with the satellite. We have microwave antennas on the satellite as well, and we can test them. We also have a vibration table. When you go up on the rocket, the accelerations that you feel on the rocket are 20 times higher than the acceleration on Earth. It's 20 G when you launch on the most powerful rocket that NASA will launch in 2 years, on which we will be part of in 2 years with Lunar Ice Cube. It will be more than that. It will be 25. That can shred your satellite into pieces. If you don't construct your satellite good enough, it will shred your satellite into pieces. It will fall apart. And we can test this. The other thing is environmental testing. We have a thermal vacuum chamber, where we can suck out the air, like we can simulate a launch. We can also shine a bright light on it. We can heat it up from one side and cool it from the other side. You have the same thing that you have in space. We can simulate an orbit, about a year worth of orbital lifetime, to in about a week. And we have all these testing facilities in Moorhead as well. Our satellite projects, one of the first ones that we launched is actually the model I have here. That is CXPN, that was launched in 2012, was looking for the cosmic X-ray background. Now, the scientific question we had with this thing was that what does the spectrum really look like? Now, since the 1960s, we know there is a cosmic background. There's cosmic X-rays coming from everywhere. Now, we need satellites. Why do we need X-ray satellites to begin with? Because our atmosphere has only 2 small windows. One is in the optical, but that's why your eyes work this way, and the other window is in the radio. That was discovered in the 1930s. So we have to launch satellites into space to come above the atmosphere, because our atmosphere shields us from all this nasty radiation that is out there. So when you look at the moon, well, there's the moon, big deal, correct? That's reflection from the sun, from the X-rays that come from the solar corona. And you see the noise around it, around the moon. Well, okay, detector noise maybe, but when you look a little bit more careful, there's a dark side of the moon, correct? There's the back side of the moon, the non-lit side of the moon. And it blocks something in the background. And that's the cosmic X-ray background. There is more cosmic X-ray, there's X-rays coming from behind the moon. And what we know today, this is coming from supermassive black holes. My background is, I'm an astrophysicist. I study supermassive black holes in other galaxies, quasars, so those are accreting black holes, where you have a very, very hot accretion disk where matter streams onto the black hole. The accretion disk gets very hot, hundreds of thousands of Kelvin, and we can see them in X-rays, and that's what you see in this picture. So we can see X-rays from quasars that are coming from the end of the universe, so to speak. That's the successor. That's CXPN2. This one was launched a year ago, went to the International Space Station on a supply flight. They bring then a couple of CubeSats up to this International Space Station, and then they release it from the International Space Station. And I will show you a little video how this works. Kent, if you're ready, if you can start this. There will be a door opening, and then it will shoot out the satellites. To the left, you will see this. Kent, are you ready? See if this works. This is a GIF file, so hopefully it works. There we go. Okay, you see that there are the CubeSats coming out. Our satellite is the one in the center. This was shot by some astronaut from the International Space Station. She shot basically with a digital camera, I don't know, 10 frames per second or something like this, but there it goes. So this is what happens. You have a spring, you have a spring loaded in this little box, like a jacker in the box. The door opens and whoosh, there goes your satellite. And it gets launched below the International Space Station. So these space station launches are pretty common. As I said, last year we had something like 400 launches. and a lot of them are launched with from the International Space Station. The big thing is, in 2 years, we are going to the moon. We are launching a mission called Lunar Ice Cube, and Lunar Ice Cube will be 3 times as big, actually a little bit more than 3 times. When I usually say, well, 1 cube is 10 by 10 by 10 centimeters, a 6 cube should be something like 30 by 20 by 10, correct? This is more a 6 cube on steroids because it's 36 by 23 by 10 centimeters, so it's a little bit bigger. It goes on the Space Launch Systems, on the SLS, on the Exploration Mission 1, which is a mission that brings the Orion space capsule to the moon. It's a test run, because a few years after that, we will bring astronauts back to the moon. And we want to look for water on the moon. It has an infrared spectrometer, so we can look for infrared spectra signatures from water on the moon. Why is this important? Why do we care about water on the moon? It's the driest place in the solar system. Well, because we want to bring astronauts back, correct? Anybody here has a water bottle with you? Yeah? That one? You know how much that costs to bring that water bottle to the moon? About $10,000. Yes. If you think you get overcharged at an airport for a bottle of water for $5 or so, or when you sit on the aircraft and they charge you $8 for a bottle or whatever, think about twice, because that's $10,000 for that bottle of water that you're drinking right now. So it is expensive. Because of that, we want to mine it on the moon. How about we mine it on the moon? The other thing is, have you guys seen The Martian? Some of you probably did. Now, what they did on The Martian was, before the astronauts actually landed on Mars, they brought a rocket down. And with the rocket, they brought down equipment that could take water, extract water from the rocks. Now, not only for the astronauts to drink, but also as rocket fuel. Because what happens, what you can do with water, you use electricity, you split water into hydrogen and oxygen. Guess what what hydrogen and oxygen is? Rocket fuel. We use the moon as a gas station. But before we can do this, we have to know where the water is, and that's the task of Lunar Ice Cube. So that's the SLS. The SLS will launch in June 2020. That's at least is the schedule. And it will be the first time that CubeSats will go beyond the near-Earth orbit, the low Earth orbit, the LEO orbit, which is something like between about 400 to about 1,000 kilometers above the Earth's surface. So this will be the first time we are actually leaving Earth gravity as well. And it is challenging. The SLS is a little bit smaller than the Saturn V that brought astronauts to the moon, but it's about 10% more powerful. It's the most powerful rocket ever built, and it will be launched again 2020 for its Virgin flight to the moon with the Orion space capsule. Where are the CubeSats? When NASA launches the SLS, NASA will also have 13 CubeSats with it on board. Some of them go to the moon, some of them go even to asteroids. There is one mission called Near Scout that has a big solar cell that uses the light from the sun to sail to a near-Earth satellite, a near-Earth asteroid. The CubeSats are in this adapter ring between the main stage and the Orion capsule. Up there you can see this. There's a ring where we have 13 CubeSats in there, and then these CubeSats will be released into space, and I have a little video from NASA that shows this, how the SLS works, and how the SLS is launched in 2 years, and then how the CubeSats get shot into space. A little pretty cute. There we go.
NASA is advancing science and technology with the first flight of the Space Launch System, or SLS. Demonstrating the capability of the new rocket and the Orion spacecraft in deep space for future human exploration is the primary goal of the mission. As a bonus, SLS will send small satellites called CubeSats to deep space destinations where they can gather valuable data for future exploration missions. Once in orbit, the SLS upper stage, called the Interim Cryogenic Propulsion Stage, fires its engine to propel Orion toward the moon. SLS will send Orion farther out beyond the moon than the Apollo astronauts traveled, where it can test communication, navigation, and other deep space exploration systems. Once Orion is a safe distance away, the fleet of 13 CubeSats will be deployed. The onboard avionics box will command each dispenser to release the small satellites, sending each one on their way to deep space destinations such as the moon or an asteroid. Each has a mission that can provide NASA with new key knowledge and test new technologies. CubeSats flown on the mission will perform in-space experiments and demonstrations that will actively advance the capabilities needed to take humans farther into space than ever before.
So one of these CubeSats will be Lunar Ice Cube, for which we will be using for finding water on the moon, which is really exciting. We are integrating the satellite right now, or we start integrating the satellite this year. We will get the components from different entities like NASA Goddard. They will provide the camera. The drive comes from Busek, from a company in Boston, Massachusetts. Now the tricky thing is when the SLS brings us there, they don't bring us to the moon. They only bring us to about 1/3 on the way, and from there we have to go. When you look at the model, when you look at the Lunar Ice Cube model that we have on our table, so please check that out when you go out here today. The thruster is an ion thruster. It's the same kind of idea. If you've seen The Martian, you know what I'm talking about. The Hermes spacecraft had the same thing, drove the astronauts to Mars. The thrust that we are getting is not enough to bring us to the moon. There's a difference there. However, what we are using is we use the gravity of the moon. There is a point, there are some points from Newton's mechanics, which you can find, where the gravity between the Earth and the moon is zero. That's the Lagrangian points. And what we can do is we can basically surf around a line where the gravity of the Earth is pretty much compensated by the gravity of the moon. And that brings us finally to the moon. We also will swing by the Earth a few times. That's why this path looks so complicated here. We swing by the Earth a couple of times, and that after about a year, we will make it to the moon. And then we will stay in a lunar orbit for about 2 months to do our measurements, and then comes the fun part. You know what we do with our mission? Huh? We crash it into the moon. We make a lunar crater. How is that? Yeah, we have to figure out a name for that. I think we have a name already, but we crash it in the moon because nothing has to stay in a lunar orbit because of the safety for the astronauts. That's the propulsion system that we use from Busek. It's a little propulsion system that accelerates ion. We use iodine ions, and it drives us to the moon. It's simply Newton's laws. There's a lot of physics involved in this. If you want to go into this field, you have to understand physics, you have to understand math, but it's a fun field. You can play with a lot of toys when you get into this field. It's a lot of fun. That's what Lunar Ice Cube looks like. At the end, all the components, again, that we have on the big satellites is on these smaller ones as well, and they get more and more powerful because of the miniaturization. Last but not least, last minute that I have, I want to mention, we have to talk with satellites, correct? When you have your cell phone without an antenna, it would be useless. That's what we use too. On the satellite, we have an antenna. We need to communicate with the satellites, and that's what we do with our 21-meter antenna. This 21-meter antenna will become part of NASA's Deep Space Network this year. NASA has 3 antennas, or 3 facilities. One is in California, the other one is in Spain, the other one is in Australia, to keep track of satellites in deep space, which means the moon and beyond. But with all these missions going into the interplanetary space, they are simply booked out. And guess where they came to? Moorhead. We are number 4 on the node, and we will become part of this entity next year, or this year actually, with 2018. And then by 2020, when the rockets will be launched, the SLS will be launched, we are ready to track those satellites. Alrighty, guys. I made it on time. Awesome. Thank you! You guys have any questions? If not, then still, yes, there's a question up there. Pardon? Thank you. If you want to see more, oh yeah.
So, you know, like the advancement that happened. Okay. So we know about the success that SpaceX made with the Falcon Heavy, where they were able to retrieve a lot of their materials. So are you guys doing anything similar, or do you plan on doing anything where you can recover a lot of your materials?
Not so far that I'm aware of. But talking about SpaceX, what you do with these little satellites is you always hitch a ride with somebody else. It's like hitchhiker through the galaxy, you know? Maybe not through the galaxy, but through the solar system. No, we don't have a project like this, but thank you.